Hello everyone, I welcome you all once again to my series of lecture that is Understanding Pharmaceutical Science with Dr. Hariharan. So today we are going to discuss about the optimization of the fermentation media. So which is on one of the important aspects while performing the upstream process of the fermentation process, because an exact designing of an fermentation media is important for an effective and maximum yield of the product. So let us discuss one by one about various optimization techniques. So before that we will get a basic understanding about certain terms like fermentation, fermentation media and criteria of the fermentation medias. So first we are understanding what is meant by a fermentation. So I have already told in my previous lecture that fermentation is a Latin term called as fervere, meaning to boil. Because the appearance while the production of ethanol from yeast in a malted grain, so it shows a boiling appearance. This boiling appearance is because of the release of carbon dioxide bubbles because of the anaerobic condition in the alcohol fermentation. What is actually happening is that in the malted grain, while the yeast consumes the glucose, in anaerobic condition it forms a highly reduced product called as ethanol and an oxidized product called as carbon dioxide. So this carbon dioxide will get evolved, so it's look like a boiling appearance. So that's why it is called as a fervere, meaning the fermentation. So if you technically see what is meant by a fermentation, so fermentation is a metabolic or a biochemical process. So what happens in this process is that the microorganism utilizes the substrate which is present in the media, then it converts into a product through its biochemical pathway, right? Otherwise we can call it as a metabolic pathway. So for example, if you see that the yeast consumes the glucose as a substrate, and through its metabolic pathway in an anaerobic condition, that is the glycolytic pathway, it forms ethanol as a product. So generally the fermentation product can be of a primary or secondary metabolite of this microorganism, which is of an industrial importance. So the next one is the fermentation media. So if you see, most of the cells, including all the microorganisms, will need water, then an energy source in the form of a light or a carbon source, then a nitrogen source, minerals, vitamins, etc. for its growth. So for each fermentation process we need a detailed investigation which components is needed for the growth or which components needed for the product formation, so that we can design a most suitable medium for that particular fermentation process. So for designing this medium, so we need to optimize the various components which is going to be included into the fermentation media. So there we need the optimization of the media, right? So if you see the optimization of the media, so it depends upon the objective. So if our objective is the biomass growth, then we need to do optimization in a different manner. So if our objective is the product formation, then the optimization will be of components little bit differ. So the optimization of the media will vary between the product formation and biomass growth. If my objective is a biomass growth, then the product formation will be considered as a not necessarily important one. If my product formation is a necessarily important one, then the biomass production need not to be necessarily important to me during the optimization process. So this optimization can be done by different methods. So if you see the different methods of optimization, we can put it into 4 categories. One is a classical method, so no longer it has been used. Second is a factorial design, generally at a low level it is effective one. And third one is the Plackett-Burman design. If more variables are there, then the Plackett-Burman design will be more helpful in the optimization process. And this design is supported by Box-Wilson method and Hendricks method for optimization. Then the fourth one is the Simplex optimization technique. So let us understand each technique elaborately. So first we will start with the classical method. So a classical method is a simple optimization technique. So in this what we are doing is that we are changing one variable at a time by fixing the other variable at a particular level. So once one variable is optimized, then it is fixed, then another variable we started changing by fixing the other variables also. For example, so if I taking a nutrient, whether it may be a carbon source, nitrogen source, or a oxygen or hydrogen source, we will change the carbon source by keeping a constant level of these other sources. So we get an optimized carbon source. Then we will started changing the nitrogen source by the optimized carbon source and other sources. Then similarly, what we will do is we repeat for the other sources. So this will continue. But the major limitation with this method is that it is a highly time consuming. It consumes, we have to perform more and more methods. If the variable started increasing means it still consumes more experiments. So no longer it is not a preferred method. So nowadays it is replaced by other methods. So one of the method is the factorial design. So a full factorial design will help to identify a particular independent variable at an appropriate level. But this design will be helpful up to a level of 2 to 3 variables. So generally up to 3 variables, this design we can perform it with a limited number of experiments. Otherwise what happened is the number of experiments which started increasing. So for example, if you perform a factorial design, so this can be identify how much experiments we need for a particular factorial design by a simple mathematical formula x to the power n. So where x is the number of levels and n is the number of variables. So if I have 2 levels, that is high and low, and I have 3 variables, then it is becomes 2 to the power 3. That means I have to perform 2 into 2 into 2, that is 8 experiments, right? So because of this changes of levels and variables, what happened is that the number of experiments will started increasing. For example, if you see the limitation of this design, if I have 3 nutrients at 2 concentration, that is 3 power 2, I have to perform only 9 experiments. If I have 6 nutrients with 3 concentration, then it becomes 3 to the power 6. So what happened is that I have to perform 3 into 3 into 3 into 3 into 3 into 3, that is 6 times 3. It takes about 729 experiments. So this is not possible. So that's why we have started looking after the other way of optimization, the techniques. So the next very useful one, which is commonly employed for the media optimization, is the Plackett-Burman design. So the Plackett-Burman design has been used because we can investigate even more than 5 independent variables, right, with a least number of experiments. So one of the other advantage with this one is, one, we can take more number of variables, more than 5, with a least number of experiments. Second, with this design we can still find out of the various variable which is most important one and which is the least important one. Then next, of this most important one, we can optimize it easily, right? So I can explain this Plackett-Burman design with a simple illustration. So let's consider we have 7 variables, okay, A to G. That means we are preparing a fermentation media. In fermentation media, we have 7 components, that is A to G, component A, B, C, D, E, F and G. Right. So out of this, what I am taking is, out of these 2 components I consider as a dummy one, because it is not going to impact my experiment. So out of this A to G, I am taking E and G as a dummy variable. So why I am taking this one as a dummy variable is to calculate the experimental error. So whether I have wrongly performed the experiment, otherwise my analytical method was a problematic one, that experimental error should be identified. This can be identified with the help of these dummy variables. Then I am taking 2 levels. One is an high level, that is the maximum amount. Second is the low level, least amount, right? Then I am constructing the design, this Plackett-Burman design. As you can see from this picture, so I have 7 variables A, B, C, D, E, F and G. Then out of this I can run 8 trials, that means 8 experiments. So in this I have put H, which denotes the high concentration, and the L, which denotes the low concentration. So in this design, let us start with the first variable A, because similar like variable A I have performed for other variables also. So in variable A, you can see if variable A is high and B is high in 2, if variable A is low, then B is low in 2. This you can see in the picture. So if A is high, A and B both are high in 2 experiments. Similarly, A and B will be low in 2 experiments. And you can see if A and B is high in 2 experiments, similarly it will apply for the others also. Let's consider C and D. So for C and D you can see 2 will be high, right? Similarly 2 will be low, right? So out of this we can 8 experiments, 4 will go away, 2 high and 2 low. And another, if A is high, then B will be low for 2 experiments. Similarly, if A is low, B will be high for another 2 experiments, right? So this will apply for all other sets of variables. So we can construct a different concentration, variable A which is high, variable B which is high or low. This will depend on it. So this will help to cancel out any variables which is having an overlapping effect on it, can be easily determined. So we will perform the experiments. After performing the experiments, we get the readings. So reading in terms of how much alcohol is formed or how much product is formed, we will get it. So we will start at calculating. So first we will calculate the dummy variable. So all the calculation, whether it's a dummy variable or experimental variable, should be done in a similar manner. So if the dummy variables reads 0, then there is no problem in the experiment. There is no experimental error has occurred, because there is no interaction or no error in measuring the response is there. If the dummy variable doesn't measure 0, if it is not equal to 0, that means there is a problem with the experimental design, especially in the experimental precision, and an error in the analysis of the product formation or response measurement. So this should be look into it, then re-perform it. For consider in our case, the dummy variables E and G is equal to 0. So then we'll start analyzing the data. If we see the various stages of analyzing the data, so in the first step we determine the sum of high values, that is 4 will have a 6 will have a high values and 6 will have a low values. So in step 1 we determine the high and low value and its difference. In step 2, we will also calculate the mean square of each variable. So if you see the step 1, this has been illustrated with a simple experiment. So what we will determine the difference between the average of high and low variable. So simple mathematical formula, sigma A H minus sigma A L. So we will get a value. This for the independent variable as well as for the dummy variables. Then similarly we will calculate the mean square of each variable. So this can be calculated by a simple formula that I have shown you. Sigma of A H minus sigma of A L whole square by, so we have 8 experiments, that's why it has been divided by 8. If it is more number of experiments, then it has been divided by particular number of experiments. So we will calculate for all the variables. So in this experiment you can see we have calculated it, that is sigma H 3.9, sigma L 14.9 and its average, that is the difference is that 3.9 minus 14.9, it is minus 11, and the mean square value is 15.125, that is minus 11 square by 8. So we got 15.125, and the same thing has been repeated for the other values. In step 3, so what we have to do is we have to this small some experimental error has been occurred because of E and G should be removed out. So for that what we have to do is the mean square of E and G should be averaged out. So it gives a value of 0.0325. How we have get it? I have shown in this calculation. So the mean square of E is 0.045 and the mean square of G is 0.020. So we add, divide by 2, we got 0.0325. Then to identify which variable is an important one, which can produce larger effects or which doesn't have any effect in the optimization process, this can be found in the step 4. So in step 4, we can identify that factor which is showing a larger effects, which doesn't have any effect. This can be done by means of the F test. So the F test can be calculated by a simple formula, factor mean square by an error mean square. That is for a factor A. So I have shown in the table, if you see values of this F factor. So for variable A, we have the mean square of variable A, that is 15.125, divided by an error factor 0.0325. We got a value. So similarly for B, C, D and F, because E and G are no need to calculate because that has been used for the error factor calculation. So we calculated for the 5 independent variables. So if you see the results, out of this A, B and F shows larger effects which have a value in hundreds, that means that are more significant in the product formation, whereas the value of C and D is not significant in the product formation. So we can do optimization only for this value A, B and F. So then the next step in the Plackett-Burman series will move on, especially to the optimization level. So optimization level is that finding a particular value of this key independent variable which is significant for the product formation. So this can be done by 2 ways. One is the Box-Wilson method and second is the Hendricks method. So how we can calculate by these 2 methods, if you can see. In Box-Wilson method, it is done by plotting a response surface curve. It is similar to that of the counter plots. So how it has been plotted is that we can plot a counter plot between 2 experimental variables. So between 2 experimental variables, what the response is, we got it, we make a point, dotted lines, then these dotted lines will be plotted into a graph. So if you see the construction of the counter plot, what happens is that we perform a series of experiments by changing the values of different variables, that we get different dots, then we make a D-line it, so we get a graph. This is how the counter plot came. So the experiments will be performed in the same results, at the same points we get the same results which are joined together until we get a counter line, right? For example, how we can get a counter line is that we are taking 2 variables, consider x1 and x2. So I will fix x1 and change the x2. So once I have plotted it, then I find the maximum product yield of these values, fixed x1 and fixed variable x2, similar to a classical method. Then I will get a best value of this x2. Then keeping the x2 as a constant, then I will change the x1. So I will get the graph. So out of this graph, we can get a final maximum yield at which concentration of x1 and x2 can provide to us. So that concentration can be used as an optimized concentration for the fermentation media. So this is Box-Wilson method. And in the Hendricks method, it is more or less similar to the counter plot of Box-Wilson method, but it has been done in a little simple level to predict this optimum combination of the 2 variables. So how this is performed? Initially the values of variable of initial experiments are chosen randomly. So you can choose any value at any point, then perform experiments. Otherwise, by the guidance of the previous experiments also, you can choose the value, perform the experiment. So Hendrik's strategy was simple, that he proposed a stepwise strategy to find an optimized concentration and an incremental fashion. So how he has done is, first he created a space. That means we have a variable x in x-axis and variable x2 in y-axis, right? So I will select 5 points at any level, right, to get a space around a plot, right, to make it a circle one. So I will run 5 experiments, right, 5 random experiments of 5 points. So we get a space. So after that, a big space, we will concentrate it to a smaller space by selecting another 5 points inside that space and running another 5 random experiments of this new space. Then we get another area, then we further reduced it, then we further run it. For example, if I am running 5 experiments in a ratio of x1 10 and x2 50, x1 20, x2 40, x2 30, x2 40, like that I have run it, then I will get one optimized concentration, that is x1 20 and x2 30. Then next point, what I will do is, I will concentrate it, x1 22, x2 28, x1 25, x2 25, like that I will segregate, make smaller of this one. So I will continue to doing this activity until it reaches to a particular point, right? So this I have shown in a simple example of a 2 independent variable of a fermentation media nutrients, cellulose and soybean meal. So in candidine fermentation, you can see that first we have a concentration of cellulose and soybean, we get a maximum one, then the circle is concentrated step by step until we reach a fixed optimized level. So this is an Hendrik's method. So whether by the Plackett-Burman series, whether it's a Box-Wilson method or Hendrik's method, so both has been helped to find with least number of experiments and optimized level, especially of the which is more important independent variable. Then the last optimization technique is the Simplex optimization technique. So this technique is with still less number of experiments than Hendrik's method, we can optimize it. So in this technique, how it is performed is that the initial experiment condition is chosen on a graph. So we take 2 points, A and B, which is an equal distance, and forms a vertex. We make a line. So this vertex we call as a simplex. So in this way we will initiate it. So what we are taking? We are taking 2 variables. By using these 2 variables, we perform an experiment. Then the distance between these 2 variables, we create another point, making an equilateral triangle. Then this equilateral triangle started going for the next set of experiments until we get an optimized level. So this is the basic idea of the simplex optimization technique. That means this has been done by a formation of a equilateral triangle in a graph. Then finally we reaching an optimized concentration. So this I will explain by a simple experiment and illustration. So consider a simplex optimization technique between 2 sources, one carbon source and one nitrogen source, right? So how I am performing is that first I am taking a 2 concentration at point A and point B. So point A we have a particular nitrogen and carbon source concentration, and point B we have a particular nitrogen and carbon source concentration. Then what we will do is we make a line which is called as a first vertex. So point A I will perform an experiment and I will calculate the product yield, right? Then similarly at point B, at new carbon source, so I will new carbon and nitrogen source, I will perform an experiment and I will calculate the product yield. So I have done it. Next what I am doing is, So the distance between A and B, another point is selected. So it has an equal distance called as another new point I have selected as C, which has an equal distance from A to C and B to C. So it produces an equilateral triangle. So we produce a equilateral triangle. Now in the graph, we got another new point called as C. So this C is a new experimental condition which has a particular carbon and nitrogen source. So what I am doing is I am running the experiment. So after running the experiment, what I am getting is I am getting a particular yield, right? So I got a product yield. So now next step, I am accessing these three values. At point A of these two independent value, how much is the product formation? At point B, how much is the product formation? At point C, how much is the product formation? So let one will be a best yield and another will be an worst yield. So out of this, I have assessed that experiment A, that is point A is an worst value, that is has a least product yield, and point B is a best yield. So out of this, what I am going to do is I am going to construct another point that is called as D. So which is opposite to A. So this is called as reflection. So it is like a mirror image. So I am drawing a centroid line to this equilateral triangle, that is A, B and C. I have a thing. In this I am drawing a centroid line. So the length of this line, I am making a reflection on another side to a point D, right? So the D point becomes a new set of experiment because it has a value of a carbon source and a nitrogen source. So what happened is the ABC equilateral triangle now gets a reflection called as B, C and D. This you can see from the figure also. So at point D, you can see that a new carbon and nitrogen source, we will perform an experiment which is determined graphically. Then we see the how much product is formed. Now we assess the 3 points. Previously we assessed 3 points A, B and C, which is best and worst. Similarly we assess B, C and D, which is best and worst, right? If one point is worst, consider B is worst, then through CD line a centroid will be drawn and a reflection of E will be created at a triangle. So this will form a series of simplex. So if you see, this series of simplex is constructed in a crab manner, one triangle to next, next, next. So this will be constructed until an optimum is reached. So this will continue until the optimum is reached. How we can find which is the optimum value is that these readings will started itself rotating, started circling around that particular optimum point. So this I have shown from the picture. So if you see in the graph, we have a carbon source concentration in X value and the nitrogen source concentration in the Y value. So the first graph is constructed between A, B and then point C has been created. So in this A was worst, then and equidistant D was created. We got a new triangle that is B, C and D. Then the next reflection opposite to C, we got a B, D and E. This was continued. So once we reach point G, which is an optimum value, what happened is the triangles got a flipping between G, H and I and G, J and I. So this G is considered as a optimum value because it's circling itself. So the final one is that the reflection of this previous one which is happening and halting the movement of this simplex equilateral triangle is considered as an optimum concentration. So this how we can optimize the fermentation media. So thank you very much for patiently listening this entire lecture of the optimization of fermentation media. So kindly continue my future lectures for a better understanding of this fermentation technology. Thank you very much.